Okay, so today we're going to start the lecture. So I just sent you what I hope to finish until today. Okay, there's a continuation on the slide as we go on. Okay, so this is just, we could say, the introduction to the course, and it contains some sort of electrochemistry at the level of the instrumental method. Okay. So if we're going to look about electroanalytical chemistry, as we could say we know it, uh, it's a group of quantitative analytical methods that are based upon the physical, electrical properties of a solution of the analyte when it is made part of an electrochemical cell. So as you could see, central to the idea here is this so-called electrochemical cell. So this is either, we could say, the galvanic cell or the electrolytic cell. Okay, so as we go on, what we're going to do is we're going to discuss the different stuff that we have here in this what we call method. So we could say electroanalytical techniques are concerned with the interplay between the electricity and the chemistry, namely the measurement of electrical quantities such as current, potential, or charge. I think that's the three main categories. Okay, so current is voltammetry, potential we could say is potentiometry, and charge has something to do with colorimetry and the relationship to chemical parameters such as the concentration. So we could say when we're dealing with electroanalytical methods, we're dealing what we call technique that are capable of producing low detection limits and a wealth of characterization. And the thing with this method, it has been used in large range of application ranging from environmental monitoring. So this usually is what in terms of the heavy metals analysis, industrial quality control, they use it, and biomedical analysis from glucose meter to determination of what we call ions in our body. Okay, and if we're going to look at this electroanalytical method, they have certain general advantages over the other procedures. Okay, so you have learned about chromatography, you have learned about spectroscopy, okay, you learn about mass spec. So each of them has their own, we could say, application. And we could say electroanalytical methods, they have general advantages over these methods, okay? And we could say the first one is something to do with the oxidation state of an element. So it's often specific for an oxidation state. So for example, if you want to determine the particular redox state, you can determine cerium-3 as compared to cerium-4. Okay, so you can find a specific electroanalytical method that just target a particular oxidation state. And then in addition to that, we could say in terms of the cost, it's relatively cheap. Okay, a portable one, the one that I have purchased would cost around, if I'm not mistaken, 2019, that's around $9K. Okay, now if you have what we call the high end bench top, it could be around 30K. Okay, so how much is that in the Philippine peso? 1 million na, right? So it's relatively we could say cheap. Compare, let's say, with spectroscopic method. Okay, I have a proposal for Raman that costs 50K. The high end is around 150K. Okay, and the last time I heard about the UVBs, that's around what, 20K. Now, the chromatography method is a little bit expensive. When we ask for just the HPLC, around 100K. When we ask for the LC system, I think last time we asked for a $0.5 million for the so-called Orbitrap. Okay, and we could say it's really cheaper. So you can survive. If you want to have a research group there in the Philippines, I think this is one field that you can thrive. Okay, because it's, we could say, cheaper compared to the other, we could say, instrument. And another good thing about this one is, in contrast, okay, to many other, we could say, methods that looks on the concentration, these provide information about activities rather than the concentrations of the chemical species. And these activities usually more of what? Physiological importance. Okay, so in physiological studies, the activities of ions such as calcium 2+ and potassium 2+, so usually in our body, they are more important compared to the concentration. So I'm not sure if you still know the difference between activities versus concentration, because that's the one that we're going to talk about tonight. Okay, so in addition to this, we could say it's a fast method. All you need to do is you put your sample and dip it in a 2-electrode or 3-electrode system, and you can get the signal right away. Okay, and you can do it on site or in situ. You can bring it anywhere. If you want to determine the heavy metals of some of the 7 lakes there in San Pablo, you can use this. All you need to do is just bring that thing. I have the, what we call like a small attache case with me of Metron. Okay, that I was supposed to bring last year to Marinduque, but some of the cables I cannot find. I think I misplaced it during the pandemic, and I never able to use it again. And this, we could say, method can provide you information. Okay, it can provide you a wealth of characterization information, such as, instance, what? The oxidation states. Okay, if you want to study some of the metal that you have or some of the system that you have, the stoichiometry, okay, the rates. So you can determine here the rate of mass transfer, okay, in terms of the stoichiometry, the rate of interfacial charge transfer, okay, as shown here, and the equilibrium constant for some chemical reaction. So the basis of this is what? Anyone? What's the basis for all of this? What reaction? So the basis for all of this is what we call the redox reaction. So imagine yourself, what you want, what do you want to do in your life? Do you want to stay as a teacher? Do you want to have a future there as a what? Future professor? So maybe you can take this into consideration as one of maybe what we call research group. I don't know if you can imagine yourself doing this in the near future. But as I've told you, I think it's affordable. Okay. And I think I owe my scientific career starting it in what we call electrochemistry. If I didn't start with electrochemistry, I don't know what happened to me. Okay. So I think I was just in the right place at the right time during the time that Dr. Santos was there in the Philippines. Okay. So if we're going to look at this electroanalytical chemistry, so if you're going to look at the method here, so you could say electroanalytical methods are divided into two. Okay. One that is the interfacial methods, and the other one is what we call the bulk methods. So what do you think is the difference between the two? Let's say the bulk method. Anyone? Usually, that's why I made the presentation short so I can interact with you. So what comes to your mind when you say bulk? Bulk properties po measures of bulk methods like mass transfer. But the way that you look at this interfacial versus bulk. So what comes into your mind when it is what we call bulk method? So which do you think is more common between the two? So between the two, I would say if you're going to look at the methods that you have here, there's so many. So this is one that is more common compared to what we call the bulk methods. In some instances, they don't even discuss about these bulk methods. They just discuss with this what we call interfacial method. Okay, so there are many types of these electroanalytical techniques that the methods that have been developed, and they are generally, we could say, useful. Okay, so when we're talking about bulk methods, usually this is the one wherein it measures the property of the whole solution. So if you have bulk method, it measures properties of the whole solution. Okay. Now, if you're going to look at the definition of this bulk method, they are based on the phenomena that occur in the bulk of solution, and efforts are made to minimize interfacial methods. So this is very different from the interfacial methods, because in the interfacial method, these are based on the phenomena that occurs. What do you think? At the interface, see, it's just a word. Okay. At the interface between the surface of the electrode, okay, and the thin layer of solution that is just adjacent to the surface. Okay, so that's the difference between we could say these two methods. Now in the bulk method, you only have the we could say conductometry or the conductometric titration. So we're going to look at the difference that we have on these different methods. And I don't know if you encounter some of them already. And if you're going to look at these interfacial methods, you would see that there are two major categories: the static methods and the dynamic methods. So if you're going to look at the static methods, these are what? So we could say the difference between the two is depending whether there is current in the electrochemical cell. So if you have static method, what can you say? Is there current or no current? Okay. So if you're going to look at this I equals to 0, so if it's a static method, okay, that means that there's no current. So this is usually a potentiometric method. Compare it with the dynamic method. Okay. So if you're going to look at the different method that we have here, so dynamic versus what we call static. Okay. So when we're going to look at the static method, it doesn't allow current to pass through the electrochemical cell. So as you could see, the value of your static methods, the current is equals to 0. Okay. And the classic example that you have there are your potentiometric methods. So if you're going to look at the unit here, so this is what potential and this is the volume. Okay. Now, dynamic method on the other hand, okay, it allows current to flow and force a change in the concentration of species in the electrochemical cell. Teka lang ha, may nakatawag para sa webinar ko. Sorry for that. Kalimutan ko sabihin sa kanya na may klase. Yung vice president. Akala ko bukas yung practice. Ngayon pala. Sorry for that. Okay, sasara tayo. Bulk and static. Okay, so bulk method we could say is just bulk method, static and dynamic method. So static method usually you don't have any current in the system. Okay, and dynamic method you pass current through it. And if you're going to look at this, okay, there are also two conditions that you have here. So one that is where you control the potential, and the other one you have a constant current. So in a constant current, you have here electrogravimetry and the coulometric titration. Now, if potential is involved here, okay, you can either have a constant electrode potential coulometry, voltammetry, amperometry, titrations, and electrogravimetry. Okay. So we're going to talk about this. And I think we try to differentiate one method from the other. I don't know if you have an idea how one differ from one another. Okay. So we can look it also in terms of this one. So if you're going to look at the highlights here, so the similarity and the difference of a number of the interfacial electrochemical techniques. So those the one in the red, those are the specific, okay, instrumental technique. Okay. And those in the what we call the blue, that shows you the experimental condition. And the one that is in green, that is the analytical signal. So if you're going to look at the signal, look what you're measuring. So for potentiometry, you measure the potential. Okay. For coulometry, you are measuring the controlled current, the current versus time. Okay, for controlled current. Now for the controlled potential coulometry, so this is the difference, right? You also measure, okay, the current versus time. So the difference that you have here, this is a controlled current and this is a fixed potential. So amperometry, you measure current. So the difference of, we could say, amperometry and voltammetry is in terms of the potential. So if it's a fixed potential, you apply it, okay, and you measure the current, that is amperometry. Now, if the potential is variable, so that is either one of the voltammetry, okay? So if you could see, there's a lot of voltammetry that you have here. So if it's a stirred solution, you have the hydrodynamic voltammetry. For a quotient solution, you have what we call the stripping voltammetry on both of them. So in the stripping voltammetry, you measure current with respect to the potential. So different potential. Okay. And in the quotient solution, you have either the linear potential, a pulse potential, or cyclical potential. So you're changing here the potential. Okay. So here, I have to show you here because hindi nalabas yung polarography dito sa previous one, right? You don't see polarography. But here you could see that, oh, there's the polarography. Because in some books, they don't discuss polarography before, but in some books, even we could say new books, they already emitted, okay, this one. But the one that is the old one, you have a book that just, we could say, focus on polarography. So why do you think it's not applicable anymore? Anyone? Why do you think polarography is not common anymore? What is usually used in polarography? Okay, the hanging drop mercury electrode. So because of what we call the environmental concerns that they have, so they try to, we could say, eliminate them. Okay, so these are, we could say, the different ones. So this is the third solution, the one that you steer. So this is the quotient solution. Usually you leave it as is in a given solution. So by just looking at how the potential is applied, okay, you have the voltammetry. So the difference between the amperometry and the voltammetry is just one has fixed potential, the other one you can vary the potential. Okay, so I don't know if you can now differentiate each of them. And we try to, we could say, maybe use some simple analogy in differentiating these methods. So at least at this level, if you have not learned it in your 137, maybe at this level, matutunan nyo na ano yung difference ng bawat isa. Okay? So, we will talk about this method one by one in the future class, but now I just try to make you understand what's the difference between this, what we call electroanalytical method. So if you have potentiometry, it measures the potential, okay, of the electrochemical cells without drawing substantial current. So if you have, we could say, potentiometry, it's a measurement of the potential difference between an indicator electrode and a reference electrode. So usually in potentiometry, you only have what? Two electrode system. So it's either, okay, a reference electrode and an indicator electrode. Okay, so it determines the concentration of the analyte. Okay, so how does it do it? What's the perfect analogy of what we call the potentiometric method? So example of this, we could say the pH meter and the ISE. So what do you think is the perfect analogy of this in real life? Do you think anything? If you're doing potentiometry, so you're just measuring the electrode potentials. So just like measuring the difference in height between 2 points in a hill. Okay. So if you're going to look at the pH meter, how does it measure the hydrogen ion activity? Although we learn it as the H+ concentration, but at this level, what they really measure is the activity. So you look at the what we call the difference. Am I right? So what do you think happen if you put your pH meter in an alkaline solution? What happened to the potential? Anyone? Hello? So tingin nyo, anong mangyayari if you put it on what we called basic solution? Will be it able to get the detect the H plus? Most likely it's not. And if you're going to do that, you're going to have what? Some sort of alkaline error. Okay? Because you put it on a basic solution. Now, another way of looking at it is, you know, a thermometer, right? So there, here in the U.S., some of the houses that most of the houses, they have this what we call thermostat. Okay, so in the thermostat you have there a thermometer, so it measures the temperature of the room. So try to imagine, okay, that your room represents what? The chemical solution. And what does the thermometer represents? Anyone? That is your sensor. That is like your temperature sensor. Okay? So the thermometer represents the potentiometric sensor. And the temperature reading on the thermometer is like the measurement you get from the potentiometric method. I think that's the closest analogy that I can have in terms of potentiometry. So maybe you can have another example, okay? But for me, I think that's how it is. Like your pH meter serving as the thermometer, and what does the thermometer sense? The temperature of the room, okay? And the pH meter sense the hydrogen ion concentration or activities. Just like an ISE, they detect whatever the ion selective electrode they're being used. Okay? Now, let's go with coulometry. So we could say here the root word is potential. Here the root word is what? Coulomb. This is not coulometry like the colorimetry. It's different, okay? That's another, we could say, method. So in coulometry, you measures the electricity required to drive an electrolytic oxidation reduction to completion. So we could say in coulometry, there is a chemical analysis where, okay, base it on the charge that was passed. So we could say there's electrolysis here. And if you're going to look at the colorimetry, it can be what? There's two colorimetry, coulometry. So it's either a controlled current, okay, or a fixed potential. So we could say it can be a potentiostatic or galvanostatic analysis, because it can be used, okay, to measure the current versus time if you control the introduction of the current, or you measure the current with time if you control the potential. Okay, so what you do is just measure the charge of your what we call sample. So how do we make use of it? Like use an analogy of this one. So maybe we could say recording the charge that passed through a certain time. Okay, so it's just like measuring the amount of water that passed through a pipe in a given time. So we could say if you are doing coulometry, so you keep track of how much of your sample pass by or generate charge. Okay, so charge is the one that is being measured here. You measure electrical charge to find out how much of a substance is in the sample. I think that's how I look at the colorimetry. Or another way of doing it, maybe if you're saving money, okay, you have ano tawag doon, piggy bank, okay? So you want to count the number of coins that you put inside. So every time you add a coin there, you keep track of the total number. So colorimetry is like counting coins one by one as you put them in the piggy bank, and you use that to measure the total electric charge that pass through a chemical reaction. So you have an idea now, or a deeper understanding of the method that maybe you have or you didn't understand during your undergrad level. Okay. So that's colorimetry. So these are the three, we could say, most commonly used electroanalytical methods. So the other one, voltammetry. So voltammetry measures current as a function of applied potential under conditions that keep a working electrode polarized. So unlike the potentiometry, this is an electrode, three electrode system. And we will discuss most of this later on, potentiometry and voltammetry. So in voltammetry, okay, or if we're going to look at the example of colorimetry, you can use it for titration. Okay, you can use it in the so-called chloridometers, silver chloride. So you just what we call measure it depending on the amount of silver chloride that you want. Now for the voltammetry, what you have here is the technique is used to observe current and voltage during the electrochemical process in order to determine the concentration of specially metal cations. And maybe one of the things that you have here is the so-called polarography. The one that has the dropping mercury electrode. Okay, so in voltammetry, that's where also most of the so-called biosensors. You have the CB, the cyclic voltammetry, and you have here a plot of current versus the volume of titron. Oh no, that's not what we call the voltammeter. So this is current versus potential. So if you have it here, E, and then current, and then you can have it like that one. Okay, so the plot of current versus what we call potential. So how do you compare this to something that is common to you or familiar to you? Anyone? Voltammetric method. So maybe you can, let's say, you can test the flow of water through sponge, right? You're familiar with the sponge. So what happened to the what we call the flow of water if you press the sponge? So you can compare the pressing of the sponge as what? Applying a potential. So usually when you press the sponge, what happened to the water? The water is what? Release. Okay. So the sponge would represent the electrode in the voltammetric, we could say, cell. Okay. So squeezing the sponge is like applying, we could say, voltage to the electrode. And the rate at which the water is absorbed or released by the sponge is like the current that's measured during the voltammetric experiment. Claro ba? Does that make sense, class? Nakikita niyo yung difference ng mga method? Okay? Now, the other three, as I told you, this is the most common one, but I also included the other three. So, in the next slide, we have here, dalawa pala yung ano dun. Okay? Amperometry. So, we could say amperometry and voltammetry, they're almost, we could say, close to one another. Okay? But the amperometry, we could say, is the difference that you have there is in terms of this, what we call the potential. So if you're going to look at this one, when you look at amperometry here, there's a fixed potential that is applied. Unlike in the voltammetry, the potential can be what? At different point. Okay. So in amperometry, there's a measurement of current between a pair, that should be a pair of electrodes at a given applied potential or voltage. So you have here the plot of the current versus the volume of titrant that is being added. Okay. So if you're going to look at, we could say amperometric measure, it's like measuring the flow of water from a faucet by looking at how fast the water droplets fall into a bucket. Okay. So if you have, let's say, a faucet that's represent your chemical reaction in a solution, so it's going to release what? The water droplets. So the water droplets, that's your electrons, and the electrons is your current. Okay. So if it's released, it falls into the bucket. So that is your amperometric sensor or your electrode. So you want to know how fast the water is coming out. So that's how I look at it in terms of comparing amperometry with something that is familiar to you. So the faucet represents the chemical reaction in your solution that generates the electrical current, and the water droplets are like the flow of the current or electrons resulting from the chemical reaction, and the bucket is the amperometric electrode. So remember, it is current versus what we call volume. Okay, so depending on the volume, it will generate some what we call current. Okay. Now, electrogravimetry, what can you say about this? What is the difference of this electrogravimetry compared to the other one? So electrogravimetry, if you look at the root word there, gravimetry. So what is associated with this word? What is associated with that? You know, in analytical, we have the gravimetric method, the titrimetric method. So gravimetric method is what? Mass. So what does it mean? So there are some deposit or electrodeposition of the mass. So you're doing here some sort of what? Weighing. Measurement of amount of metal deposited during electrolysis. So parang nag-electroplating lang tayo. Right? You know the soldering, di ba? Sometimes magsa-solder ka, nag-electroplate ka lang. Okay? So the way I compare it in an everyday life is paano ba? Electrogravimetry. So the way I would say it is maybe when we eat, if we gain weight or not. Okay. Because the way that you do is you try to look at the substance, if it's being deposited on the electrode, and you're going to measure the electrode's weight change to find out how much of the substance was in the solution. Okay? Wala akong ibang maisip na electrogravimetry eh. Basta anything that you wherein you can get there's a change in the mass that proportional doon sa material na meron ka. So you're using electrolysis here to deposit, okay, or maybe to convert whatever metal ion that you have there and then convert it to metal in your what we call electrode surface. Now the last that we have here, conductometry. So this is from the bulk method. So this is the method in which the capability of the analyte to conduct an electrical current is monitored. So ang basis dito, Ohm's law. How do we write Ohm's law? Okay, Ohm's law is potential equals to current times resistance. So here it is apparent that the electric current is inversely proportional to the resistance, where E represents the potential difference. So the inverse of the resistance is the conductance. And as the conductance of a solution increases, its ability to conduct an electric current increases. So conductometric measurements require the presence of ions. Ions and conductometry is not useful for the analysis of undissociated molecules. So it only works if your sample is dissociated. Okay, why? Why does it has to be dissociated? Anyone? Look at the word. Okay, for it to become conductive. Okay, and you don't need it to be in the surface. It is usually in the what we call solution. So nakapasok na iba? Kasi kumpleto na tayo eh. So those are, we could say, the different methods. Conductimetry, how do we, what we call, compare it in real life? So maybe try to imagine a bridge that's made up of different materials. So let's say wood and metal. So when you walk on it, what will happen? The sound that it makes depends on the material of the bridge. So conductometry is we could say like listening to the different sounds the bridge makes to determine the materials it's made of. So it depends on kung ano yung materials mo, magka-conduct siya ng electricity. Okay? So that's how we could say the different methods in electroanalytical techniques or chemistry, and they are being used upon it. Now, what we're going to do for the rest of the meeting and continuation next week is we're going to look at the so-called electrochemical cells. Okay, so if we're going to look at these electrochemical cells that we have, so if we're going to look at the electrochemical techniques that we have, what can you say about them? Are they what? Homogeneous or heterogeneous? Before we could say, I go to that one. Okay. So if you're going to look at the electrochemical or analytical measurements here, what do you think they are in nature? Homogeneous or hetero? What do you think? So usually if we're going to look at this is the electrode. Then what happened? You have the electrolyte solution. So here pala, makikita nyo na kung homogeneous siya or heterogeneous, di ba? So an electrode is usually what? A solid, and you have an electrolyte solution which is a liquid. Okay? So if you're going to look at this, usually there's an exchange that happened there. So ano yung nangyari dito? Oxidation reduction. And from this, what will happen? You're going to generate the electron. And usually, we could say one of the things that comes out here is this relationship. So there are some factors that affect the so-called electrochemical measurement. What could be those factors? The materials of the electrode, okay, the electrolyte solution. Does that make sense? Ano pa? What do you think the other factors that can affect them? So maybe, saan sila nag-i-interact? Doon sa interfacial or sa surface. So the surface cleanliness might affect them, or the surface chemistry will also affect them. Okay, so when we go one by one, we look at how the electrochemical or analytical measurement is being done doon sa potentiometric method and voltammetric method. But this is how the electroanalytical measurements is being done. So yan lang yun. We could say the chemistry or science behind of this method. Okay. So I don't know if this pique your interest. Okay pala tong electrochem. But I think walang electrochem ngayon dyan. Kasi kung meron, hindi ako nagtuturo nito. Okay. So, electrochemical cell usually consists of what? Two electrical conductors, and we call them electrodes. Okay, so these are the electrodes, and they are immersed in, anong tawag natin sa solution na to? Electrolyte. Okay. And for a current to develop, they said there's three things that you need to do. Okay, and I think I put it around here. So you have the electrons within wires. Okay. So it is necessary that the electrodes be connected externally with a metal conductor. Okay. So this allow you to the electrons to travel. So you have what we call some wires here. And then the other, we could say, time that there's a conduction in the cell is the ions within the solution of each half cell. So you have the anions and cations, and they pass through the salt bridge migration. So this one on this side and that one on the other side. And then last but not the least, the redox reaction that happens in the electrode surface. So one is the one here. The second one is the one here. Okay. And the third one is the one in the surface. Now, if we're going to look at this, I have three electrochemical cells. So what's the difference of this so-called electrochemical cell? So here we have an electrochemical cell that is at open circuit. So what do you think is this? Galvanic electrolytic. How is this different from the second one? Okay. So is the first one the same as the second one? Look at the, what we call this one here and this one here. In what way they're this, what we call different? So all of them we could say are of the same electrode. You have silver and copper, and you have silver nitrate solution, copper sulfate solution, silver nitrate solution, and copper sulfate solution. Okay, so what's the difference between the two? So here I told you this one is in open circuit, this one is doing work. Okay. So if you're going to look at the two solutions, they are joined by what? the salt bridge. Okay, and the two ends of the tubes are pitted with the porous plugs or discs that permit the movement of ions across them but prevent siphoning of liquid from one electrolyte solution to the other. So you can have a salt bridge like a paper towel, okay? We just what we call put it in a saturated salt solution. So what do you think is the purpose of the salt bridge? What does it do? In your Gen Chem, salt bridge is what? Maintain electrical neutrality. But what do you think it do here? So usually the salt bridge, okay, the purpose of this salt bridge is to isolate the contents of the two halves of the cell while maintaining electrical contact between them. Okay, so you need to isolate. So it isolates the contents of the two cells, two halves of the cell, while maintaining electrical contact between them. So why do you think isolation is needed? Why do you have to separate them? To have a difference in potential? Imagine if they're just in one what we call cell. You don't have the salt bridge. What do you think will happen? Okay. So here, the reason why they have to be isolated is to prevent the direct reaction between the silver ion and the copper electrode. And if you're going to look at this, I can introduce you to this concept of liquid junctions. Are you familiar with this term? So how many liquid junctions do you see here? So in what we call later on, we have a slide for the term of liquid junction. So here we usually have two liquid junctions. Okay, the first one is being the interface between the silver nitrate solution and the salt bridge. So there's an interface here, the silver nitrate solution and the salt bridge. Okay, where do you think the other one? This one. So those are the two, we could say, liquid junctions. So later on, you will see when there's only what? A small one liquid junctions in a given cell. Okay, now, how is this different from this one? Do you see the difference here? So meron ka ng, ano dito? Battery source. So this is now what? That's now an electrolytic cell. Okay? So yan yun, we could say difference nitong isa doon sa dalawa. But look at the composition. Is it the same as the previous two? So if you're going to look at the previous two, you have a silver electrode and a silver nitrate, a copper and a copper sulfate. So if you're going to look at this, they're the same. But the thing is now, look at the flow of the electron. It is now going on the other side. Okay? So if you have here, this is what? Already an electrolytic cell. So how are we going to compare the electrode process that is happening here? So if it's what we call here, what could be the cell reaction that is happening? So maybe we're looking at now the conduction of this, what we call in cell. So how is the reaction happening here? So the first one they said is between two electrodes. So it is between what? The copper. Let's go on this one first. And the silver electrode. So here we could say the electrons are the carrier of charge, moving from the copper going to the silver electrode. So that's we could say where there's conduction in the cell. Now the next one is within the solutions. Okay, so within the solutions, the flow of charge is the result of the migration of cation and anion. So in the half cell of the left, what do you have here? What could be the reaction that is happening here? You have copper 2 plus. What happened to the copper 2 plus? At least here in this electrochemical cell. So where do this go? Because the next conduction that we have is ions within solution of each half cell and through the salt bridge. So this one will go, the copper 2 plus will migrate away from the electrode into the solution. So what are the ions that you have here? Copper 2 plus and sulfate ions. Here you have silver ion and nitrate ions. And what else the ions that you have here? So you have a K plus and a Cl minus. So all of them, since they are charged particle, they participate in the flow of the charge. So that's the second conduction that you have. The first one is the electron from copper here going here. And the second one is the flow of the charges that you have from the ions once they form into a solution. Now, the third one that you have here, that's the one that occur in the surface. So what's the reaction that you have here? So that is the half reaction as we know it sa Gen Chem. So what's the reaction that you have here? Copper producing copper 2 plus 2 electrons. And this one you have silver ion reacting with electrons to produce silver. Now, paano kapag dito sa kabila? How is the half reaction there? So ano nangyayari dito sa copper electrode? Okay? So it becomes now the other way. So the copper is the one that is being oxidized. And this one is the one that is, we could say, reduced. So if you're going to look at the overall reaction, so here, it's copper And on the other side, it's the reverse. Now, both of them, we could say, has the same composition, right? They have the same, we could say, electrode. The only one that's different, one is you provide the source, and the other one, it produce or do its work. So that's the difference. If you have a source that you can provide, you can make the reaction backward. Okay, and by definition, okay, what do we call this electrode here? Ano tawag dito? Anong odd? This is your what? Anode. And this is your cathode. Now, in the electrolytic cell, is it the same? This now is your what? Anode. And this is your cathode. So the anode is always where we could say, teka, nagkamali ata ako. This one should be, try to make sure. Yeah, I think this one should be this becoming this one, and this one is the other way around. Pareho pala yung reaction na sinulat ko eh. So copper, copper 2 plus, and this one copper 2 plus to copper. So this is the anode, this is the cathode. So that's the difference that you have. So hindi nyo ako kinorek. So this is a copper 2 plus 2 silver, producing copper and 2 silver ion. So dapat they have this what we call reverse reaction. Okay? So this is just more on, we could say, looking at it in a much deeper way. So now you see how the conduction happens. So the flow of the electron from the metal, okay, the flow of the ions, okay, in the electrolyte and the salt bridge, and the reaction that happens in the electrode. Okay, now if we're going to look at the half reactions that we have here, so we could say this is the cathode half reaction. So you have your copper, okay, if you have your Fe3 plus, if you have a silver. So this is now when you have this system that you have. I think this is not. So in a cathode half reactions, like the example that we have here, so this is where reduction happens. So the electron is supplied by the electrical current via the electrode. And the species can both be in solution, solids, or coated on electrons like this one, silver, silver chloride, or a combination of copper 2 plus and copper solid. Now, the anode, on the other hand, as you could see, the electrons are on the product. The electron is taken up by the electrode in the electrical circuit. Okay, so that's, we could say, a more specific example of the half reaction that is happening. Now, when we're talking about the liquid junctions, that's just the interface between two solutions with different components or concentration. Okay, so here, as I told you, okay, the different, we could say, liquid junctions is the one between this one and the one that is here. Okay, because you have here two different solutions. So you have your silver ion solution with nitrate ion with the salt. And on this one, you have the copper ion and the sulfate ion with the salt. So you have here, we could say, two liquid junctions. Okay, so that's what it means when we're talking about liquid junctions, the interface between two solutions with different components or concentrations. Now, do you have an interface between this solution and this solution? May interface ba itong solution na to at ito? Yes or no? So it has to be solution close to one another, but they're not close to one another. You have to pass through the salt bridge. Okay. Now the question, can you have a galvanic cell without liquid junction? Is that possible? The answer is yes. Okay. I'm not sure. You can have a cell without liquid junction. Okay. You can have a cell wherein a galvanic cell wherein you have what? Two species that have high potential for reaction. Okay. But the problem is what? Mabagal yung what we call reaction nila. Okay. So you can mix two species directly into a common solution, but you don't commonly do this thing. Okay. So we could say an example of liquid junction or a galvanic cell without liquid junction is the one that we have here. So what cell is this? What are the components that you have in this cell? Ano yung cell na nakikita nyo dyan? Anyone? So you have here what? A silver electrode and a platinum electrode. Now, why is it there's no liquid junction there? Because there's no difference in the composition of the solution. Okay, remember the definition of a liquid junction interface between two solutions. Do you have two solutions here? You only have one solution. Why? Because you only have one container. And what's the solution that you have there? The one that contains, okay, silver chloride. So if you have this, what we call the cells without the liquid junction, okay? So what type of cell is this one? What do you think the type of this cell? You okay? Nahawa na sa'yo eh. So how would be the reaction here? Give you water? No, just put in my glass, my mug there. So anyone, what do you think is the reaction that is happening here? So there is a redox reaction here. As you can see here, which is the anode? Can we say this one? And this is the cathode. And what's my basis? The electron. The electron will always travel from A to C, anode to cathode. So what is happening in the anode? So it's the reaction here that you have what? H2 producing 2H plus. Tama ba ako? And the other one, you have what? How is the reaction for this one? So this is the anode that you have, and this is the cathode that you have. So which do you think there is the reaction that is happening in the cathode? Is it this reaction or this reaction? So as you could see here, if you're going to have the voltmeter here, okay, this is how you're going to do the reaction. But if you're going to replace your voltmeter with the wire, what do you think will happen? Your silver will behave as the cathode. Now, what do you have here? So you have the AgCl on this one. Okay, that is the one that's happening. There's also a silver ion that is happening there. Can you combine these two? If you combine these two, what happened? Cancel this, and you end up with HCl. Does this make sense? Plus E producing Ag plus Cl minus. Tama? The one that is happening is the sum of these two reactions. Yeah, but as you could see, if you're going to add them, okay, you cannot, the first reaction is essential for the second reaction to happen. But what's really happening here is the net reaction. So we could say you have here AgCl reacting with, we could say 2 electrons, so we can just put 2 here, producing 2Ag plus Cl minus. And overall, the reaction that is happening here, okay, 2 silver chloride reacting with H2 to produce 2H plus and 2Ag plus, that's 2Cl minus 2Ag. So this is the reaction that happens when you have no liquid junction. So you could say, interestingly, what happened when you have liquid junction, no liquid junction, you can have a two-step process that is happening in the surface. So here, you could see silver chloride producing silver ion and chloride ion, and then the silver ion will reduce to form silver metal. Okay, so you form here, we could say your slightly soluble chloride, it dissolves in the first step to give you silver ion, and then it forms into a silver metal. Okay, now you can also say that this can also be a two-step reaction or two-step process. How does it happen into a two-step process? So maybe your H2, that is gas, okay, you're going to form what? What do you see here? You're going to form under H2 that is aqueous. And then what will happen? Your hydrogen that is aqueous, that's in the form of the bubbles, is going to give you 2H plus 2 electrons. So there is, we could say, also a two-step process that is happening in the anode. Okay. So what do you think is this one? A galvanic cell or an electrolytic cell?
Galvanic cell.
Okay, so this is a galvanic cell.
Galvanic cell.
Now, if you're given this one, we could say that you cannot tell whether a given electrode will be cathode or an anode unless you know whether the cell is what? Galvanic or electrolytic. Okay. So this is the one that a galvanic cell that you can have even without this what we call liquid junction. Now, the last I think I'm going to talk about here is the solution structure, the so-called electrical double layer. Okay, so as I've told you earlier, usually we have a heterogeneous system in an electrochemical measurements. And in this, we could say system, the electrode can only donate or accept electrons from a species that is present in a layer of solution that is immediately adjacent to the electrode. So remember the way I put it, electrode and the electrolyte. And usually you can do it as oxidation and then reduction. So oxidation is the loss of the electron. Okay, so if it's the other way around, so the electron will go to the surface or the electrode surface. So we could say this layer may have the composition that differs significantly from that of the bulk of the solution. So when you say bulk solutions, the whole solution. Okay. So the one that interact, if we have this interfacial thing, is the surface of the metal electron with some solution layer. Okay. So the surface of the metal electrode is shown as having an excess of positive charge as a consequence of an applied positive potential. So you can generate the positive charge if you apply this what we call positive potential. Okay, so we could say the interaction that is happening there is between the electrode and the solution surface. So what happened usually here, if you have the charged solution, usually these layers consist of two parts. You can have the tightly bound inner layer. And if you're going to look at this tightly bound inner layer, okay, the potential would decrease linearly with distance. So this is the electrode. Okay, so this is the solution layer that you have. And this is what? The bulk solution. Okay, so the surface of the metal electrode, they have, we could say, an excess of the positive charge. So that's the positive charge that you have there. Okay. So what happened there, this positive charge, it happens because of the applied positive voltage. So the charge solution layer, we could say, consists of two parts. One that is the compact inner layer. Okay. So we could say that's the one from here, D0 to D1. And then the other one is what? The diffuse layer. So this is from D1 to D2. So we could say this is what? The compact layer. And this is the diffuse layer. So what happened? Okay, in the compact layer, what happened here is the potential decreases linearly with distance from the electrode surface. So there's a decrease, okay, in the potential. So as you're going to look at here, this potential here from the surface, as you go to the compact, it decreases, okay, from the distance. And it will continue to decrease until it goes to what we call the diffuse layer. And when there's an entire array here, because what happened? What really happened here if you form the positive charge? Usually, you going to attract the negative charge on it. Okay, but you can only do that if you are what? Close. Okay, like in the compact layer. But if you are already here, it will not cause any, we could say, changes in the what we call charges. So if you're going to look at it, look, almost all the positive is near there. But as you go here, okay, the charges are already well distributed. As you go through far away from the electrode surface, okay, you will see there that the potential already decreases. So this is what we call the electrical double layer. Okay, entire array of charged species particle and oriented dipoles like the water molecules at the electrode surface interface. So that's the electrical double layer. Okay, so I think I'll end here, and then the next thing that we're going to do is the Faraday and the non-Faraday, we could say, current. So question, as we try to what we call understand what is really happening here. But as I have mentioned to you, this is a very good, electrochemistry has a very high potential. And unfortunately, the only one that I know, I think there's one in Diliman who's doing this, but there's a guru in UST. I'm not sure if you're familiar with Sir Fortunato Sevilla. He had a big, he's old. He's a contemporary of what we call Sir EJ. So they do sensors. That's what they do. Okay. And the sensors that they have is really, before they just have potentiometry and voltammetry, but now even piezoelectric. So they have this quantum microbalance where it's just like an electrogravimetry. So it can detect a very small amount of your target analyte. So it's a really, we could say, a vast field with large potential. If you can make like a sensor similar to the sugar sensor, that's small. Okay, it's really, we could say, the potential that it has is really large. And I don't know if you use who's that? Franco has a potential stat, I think, and it's just using strip. Everything is just like a drop. Okay, so there's a small strip, like a sugar strip, and then you put there the solution and you will see it. Okay, so I don't know if you plan to stay in the academy, you can think about doing this research, because its potential is really, we could say, high. I remember my friend of mine in PNRI, I think one of the biggest regrets that he had is I didn't continue with electrochemistry, because he had a lot of idea. I said, okay, we can detect shabu. All you need to do, you go to the restroom and then dip the paper strip and then see if it is what we call positive or not by putting it in the small potential stat, because you can have a potential stat that is small. The one that I have for Metron is just like this big. Okay, so the potential that it has is really good, and hindi ko alam bakit hindi nila take advantage yan sa Pinas. So question, Carmel, may question?
Sir, ano po?
Magamit mo to sa med school. Mag-develop ka ng
nagkaroon
sensors.
Sir, nagkaroon lang ako ng identity crisis kanina doon sa conductivity. Kasi I remember, meron sa 18.1 na conductivity ng acetic acid. Like, instead na mag-measure kami ng pH directly, so conductivity yung ginamit namin. And bigla akong naisip, bakit parang same lang yung nangyayari sa yung conductimetry and potentiometry.
Potentiometry. But I mean, the thing with this one, even one setup, you can fine tune it to different what we call the method. You just need a potential stat or galvanostat that you have. So question, doon sa mahina yung tawag doon? Signal. So, hindi ako makapasok sa canvas. Ano ko na ha. So I don't know if you answered my question there. The BARD and the what do you